Okay, good morning to everyone. Sorry for the delay because there's another class using this class because their original class has problem. Any question for the last lecture before we start? Any question you want to ask? Yeah, feel free to ask because maybe others have the same question. Any question you want to ask? You want me to clarify before we start? Have a look when you download the lecture notes. Maybe I will keep updating based on any feedback or mistake I found. Okay, so look at the latest step. Questions? Want to ask before we start? Okay. In that case, let's recap what we did last time. So last time we introduced an idea of span. Okay. So whenever we talk about span, we need to talk about span of a field vector here. Okay, so maybe we talk about span of a field vectors here. So what are these VI? So these are some vectors in Rn, for example. So how do we define this spans? What are inside here? What are the things inside here? What's the keyword? Set of linear combination. Okay, linear combination of what? Combine, right? You need to combine things. Combine what things? Combine these VI. But how to combine them? What the linear refer to? And how do you combine these things? You take scalar, multiple of them, and then you take their sum. Okay. Sum of a scalar multiple. Okay, where do we pick this scalar from? We pick the from real numbers. Okay, in this case, our vector live in Rn, so we take scalar from real numbers here. Okay. So this is the idea of span here. So if you want to ask a question whether a vector, okay, whether a vector live inside this spans or not, actually is equivalent to solve the system of linear equation. So to solve a system of linear equation, how do you understand it? How many ways to understand a system of linear equation? You can understand it as a augmented matrix, okay, or matrix equation, ax plus b, or vector equation. Okay, so there are a few ways to understand it. But to solve it, you can use row reduce method to solve, or you use algebra method, right? Substitution, or you use geometry. But geometry, maybe you won't get the exact point. Maybe you will know whether there's one solution or no solution. But if there's one solution, you need to pinpoint down which point is that. Then maybe you need algebra. Okay. Any questions so far? Yeah. Any question? Okay, so if no question, let's start today's content. So next up, after span, we will talk about linear independence. Okay, so independence means what? There's no relation. Okay, so what kind of relation we are hoping for here? Some sort of linear relation here. Okay, let's see what's the linear relation here. So look at this definition here. So a set of vectors, okay, again, Vi to Vp in Rn is said to be linearly independent. Okay, linearly independent. So maybe I said it. Okay, linearly independent if. So we don't know what is linearly independent, so we look for this if. Okay, so if what? If let's say you have this linear combination equal to 0, okay, so this is somewhat equivalent to solving what? The homogeneous linear equation. Let's say this homogeneous system here will imply that Ci to Cp has only the trivial solution, only 0 exist. So well, do you see that if I put 0 times v1, 0 point v2, 0 until 0 times vb, you must get 0. So this is one of the solution. If this is the only solution, okay, then we will say that this set of BP is linearly independent. Okay. So if there's more solutions such that not all of them are 0, then they are linearly dependent. Okay, let me give you an examples here. So let me give you examples. So let me give you example. Examples here. So we claim that the set 1, 0, 2, 0 is linearly dependent. Okay, linearly dependent. Meaning what? Meaning what? Meaning if C1, so meaning, so let me write this. So that is, there exists, okay, C1, C2, not all 0, such that C1 times 1, 0, C2, 2, 0 equals to 0. Can you find C1, C2 such that when you add these two vectors up, they get 0? Can you find it? Try. What C1 and C2 you can pick other than 0 to make this equation? 2, 1. Before that, does anyone curious what is this? I think I repeatedly using it, forget to tell you what is it. That exists. Okay, so this is the example of the exists. Why is it that exists? Do you see that this looks like a inverted E? Right, it's an inverted E because in old days they use a typewriter. So they can't create new symbol. So they just take out the E button and then twist it. So that's why. So the exists C1, 0, not 0. Okay, so what's the choice here? We can pick C1 to be -2, sure, and then C2 to be what? Good. That what am I doing here? C2. So if you want to choose C1 to be 2, C2 to be -1, also can. Okay, also can. Doesn't matter. But did you see that? What's the problems here? This implies what? Okay, so this implies that actually 2, 0 is a multiple of 1, 0. Okay, so you can see that one vector is actually dependent on the other vector. How to depend? Use scalar multiplication. So imagine you have more, okay, more sum here. You can write one vector as a finite sum of scalar multiple of each other. Okay, so this is why we say dependent. So that's why we look at this homogeneous equation here. Yeah, because we can move the other vector to the other side. And C dependent or not? Okay, one vector is dependent. Okay, if this C has to be 0, then there has no relation. Okay, there's no relation. So for example, in this case, so let's give you an example. Let's say this, the set containing 1, 0 and 0, 1 is linearly independent. Okay, it's linearly independent. So meaning what? There's only C1 equals C2 equals 0, such that what? C1 times 1, 0 plus C2 times 0, 1 to be 0. Okay, so there's no relation. Okay, so there's only one way if you want to add them up to 0 is when C1 and C2 is 0. So how to prove it? Okay, how to solve this? How to show that C1, C2 has to be 0? Okay, remember that this is what? You need to, okay, whenever you see this equation, right, you need to ask yourself, is this a vector equation, matrix equation, or linear equation? So in this case here, what is this? This is a vector equation. Okay, so this is a vector equation. So what can you do here? There's few ways to do it, right? Either you see it as a matrix straight away. Okay, so maybe I use the other, okay, use this color actually fine. So how many ways? Just now I told you. So one way is use matrix to see it. So this is a matrix. So here the 0 here actually is 0 bar. So better I write out the 0 vector here. Let me see. Okay. Right. So so here is a matrix equation. Okay, so if you want to see it as a vector equation, how do you see it? So you get C1 0 plus 0 times C2 equals to 0. Okay. Remember that when you want to take a scalar multiply with vector, what do? You literally apply the scalar to every term in your vector. Okay, so from this vector equation, what did you get? C1, C2 equals to 0, 0. Then you will straight away get your answer, right? You straight away get your answer. Because for this two to hold, you would have to have C1 equals 0 and C2 equals to 0. Okay. But how about matrix? Matrix equation here, what do you need to do here? You have to do what? Do the augmented matrix here. Okay, but can you see that? What form is this? Did you see a Seng test here? So this is a echelon form. Not only echelon form, right? This is a reduced row echelon form. So meaning what? You can read out the solution. So what's the solution here? C1 times C1 plus 0 times C2 equals to 0. 0 times C1 plus 1 times C2 is equals to 0. So you also read the solution already. Can or not? So remember, remember in this matrix, what's the column representing? The columns are representing the coefficient of 1 n. Okay? Yeah. If you forgot, please go back to the last chapter and then try and redo the example again. Okay? So they are really same calculation, but we put in a different language. Why different language? Because it will be useful later. Okay, we try to make more generalization. Okay, so any question for this part? Okay, linear independent. Okay, okay. So for this part, what did you notice? If you look at this two vector here, what does it mean by 2, 0 equals to 2 times 1, 0? So meaning 2, 0 is a scalar multiple of 1, 0. Scalar multiple means what? You scale the vector, so the vector become longer. Okay, become longer. Okay, so 2, 0 have length 2, and then 1, 0 have length 1. Okay, right. And then this is true for any two vectors that are linearly dependent. Okay, when you talk about, so let me quickly show you. We won't go deep, but let me quickly show you a fact, a very important fact here. So let V and W in Rn. Okay, so if there is a relation between V and W, okay, a linear relation. Okay, what can we see here is we can write v equals to minus x2 over x1 w. Okay, so this is the multiple that you. So what's the picture here? So let's draw a picture here. So if you have linearly dependent relation between two vectors here, really they need to be scalar of each other. That's all. They must be opposite. Direction can change or not if you scale it. Can you change the direction? And actually you can. Actually you can. How do you change the direction? Let me give you. For example, 1, 0. Let's say this is 1, 0. Can you get to minus 1, 0? Right. So how do you do it? You scale by minus 1. Okay. So if you multiply by negative number, the direction change. Yeah. Is it true? Is it true? So negative 1 here, right? Okay. Maybe let's use 1, 1 in this case because we are using the diagonal line. Okay. So if you multiply by negative 1, you will get a direction. Okay. Okay, any question? Okay, so if you multiply by a negative number, the direction changes to opposite. If you multiply by number greater than 1, then you make it longer. Multiply by less than 1, make the vector shorter. What happens if you multiply by 1? The vector doesn't change. Okay, it's the identity. Okay, good. So this is about linearly independent. Okay, next. And maybe this part I left as a exercise. So this question here we just left as exercise. Okay, maybe we can discuss quickly verbally how to do this. So if you want to show that this the column, okay, the column of A. So column of A means what? You split the vector, your matrix into column vectors, and then you want to show that they are linearly independent. Meaning what? You want to row reduce this. Okay, row reduce it. Okay, so if you row reduce it, you are solving for the C1, C2, and C3. So what's the question here? If. Okay. So what do you expect? What do you expect for your C1, C2, and C3? If C1, C2, C3 has only 0 solution, meaning these columns are linearly independent. Okay. If C1, C2, C3 have more solution than the 0 solution, then they are not linearly, or in other words, they are linearly dependent. Okay? Yeah. So I try left as exercise. By the way, if you try out the exercise and then look at my answer, right? You think that my answer is mistake, then tell me. You can see, we can check. And I can correct it so that people will know. Next, so what's the theorem here? The columns of a matrix A are linearly independent if and only if the equation AX equals 0 has the only trivial solution. Or if and only if every column of A is a pivot. So the first if and only if somewhat you see from the example we calculated already, right? But can you see that actually what we did just now, there is a column that is pivot. I mean, every column of A is a pivot column. See it just now? Yeah, from this case here. So how many columns here? So there are 2 columns here, right? And then every column is a pivot. Well, I think so. There's an extra condition here, if I'm not wrong here. So let me think. I told you. So I think there's a condition here. The number row A. Let me put a extra condition here. I think there's an extra condition here. Even the number of column and all equal the number of A. Okay. So I mean, you cannot, for example, let me give you this example here. Okay, so you cannot expect these two to be pivot also, right? Okay, so there are most. So you can see that the number of pivot, right, is controlled by the number of column, also controlled by number. Does it make sense? So to be a pivot, right, you need to be at least be a leading entry. But what is leading entry? Is the non-zero entry from the leftmost. You cannot make these two as a pivot. Okay, and I think, yeah, I'm not sure you can see now or maybe later. Okay, later you can see that. Later you can see what if you have more vectors than your. Later we will define what is called dimension. So you have only three entries here. Okay, but you have 5 vectors here. So these 5 vectors must be linearly. Later we'll make this precise. This idea about dimension. This is the idea about dimension. For example, maybe I can quickly give you an example first, okay, to motivate you. So for examples, let me make it shorter, maybe 1, 0, 0, 1. Okay. So you see in R2, if I pick more than 2 vectors here, they have to be linearly dependent. Okay. Maybe you give me the third one. Can you give me a third one? 2, 2, right? Okay, 2, 2. So you can see that 2, 2 can be expressed as a linear combination of the previous two. Can you do it? 2, 2 equals to 2 times 1, 0 plus 2 times 0. Okay, so this is the idea about dimension. So if you have more vectors than your dimension, okay, so in this case here, how many are here? For now, you can see as how many entries here first. Later, we will define dimension. If you have more number of vectors than your dimension, then they will be linearly dependent. Okay, it will be linearly. Just appreciate this example first. I haven't make it precise. Later, we will make this concept precise. Okay. All right. Okay. Good. Maybe this one also left as exercise because we have two similar examples. Okay, let's go to the other theorem. So look at this theorem here. A set of two vectors v1, v2 is linearly dependent if and only if one of the vectors is a multiple of the other. The set, so in other words, so if and only if. So you guys know how to read if and only if. So before if and only if is a statement, after if and only if is another statement. Okay, so this is equivalent. Okay, this is equivalent to not P if and only if not Q. So that's why these two sentences are equivalent. So you see, the first part is independent here. Okay, the second part start with, sorry. First part is linearly dependent. Okay. Second part is linearly independent or not linearly dependent. And then the other part, one of the vector is a multiple of the other. So what is the negation of this statement here? Or neither of the vector is a multiple of the other. So these two sentences is the same. Okay, because of this logical equivalence here. So do you understand what this sentence is trying to say? Actually, I show you this example already. So if two vectors are linearly dependent, meaning what? If you set up the linearly dependent equation, the homogeneous system, which is what? C1 V1 plus C2 V2 equals 0, implies C1 and C2 have to be 0. Okay, then what? Then one of the vector is a multiple of the each other. Okay, actually I show you this proof already, which is this one. Okay, if they are linearly dependent, then they are multiple of each other. Does it make sense? Okay. Yeah. Okay. If neither of them is a multiple of each other, meaning what? The only solution that solves this is 0. Okay, so they are linearly independent. Okay, so what's the main point here? Main point is this. Okay, you need to set out your homogeneous linear system first, and then you ask yourself, what kind of solutions? Then if 0 is the only solution, they are linearly independent. If there are more solutions, they are linearly dependent. Why they are linearly dependent? Because we can write them as a linear combination of each other. Okay, examples. Okay, you meet. I mean to appreciate these definition, right? You need to understand examples. You need to have examples in your mind. Correct or not? Is it true? Is it true? When I ask you something is delicious, what do you think of it? Sanai. Can you share to us what does delicious mean to you? You don't know? Do you have delicious food before? No. So what sort of delicious food you have? Okay, let me string down the target. Do you have some delicious food in Malaysia before? Which food you think is nice? Sorry? Naan cheese. So you see, when I talk about delicious, right? Delicious is like very abstract idea. But where does it come from? Naan cheese. You buy naan cheese or not? You can go to the mama nearby, right? And order a naan cheese. So to understand this definition and abstract idea, right, you need to have these examples in your mind. Okay? How we mathematicians learn it is we start with example first, actually. Although we introduce you idea, we tell you, oh, linearly independent. But actually, we see this first. Okay, so example is really important. Okay. So now actually is a very mature discussion here. So meaning what? We talk about idea first. Okay, after we talk about ideas, then we talk about how to do it. Okay, instead of I tell you, do it first, do it first, do it first. Do it first. This is the Asian thinking. The parent ask you. 先做先做先做. Okay. So we talk about idea first. Okay, talk about ideas and then we talk about how to do it. Okay. So please don't be bothered if you don't understand the idea first, because I will tell you how to do it in the second step. All right. Next up. So next theorem. So let's say we want to include more vectors into our set here. So V1 out to VP, 2 or more vectors here. It's linearly dependent. So when does it happen? If at least one linear combination of the other. Okay. Maybe again, and maybe. So let me give you a heads up here. So maybe just now we showed that 1, 0 and 0, 1 are linearly independent. Okay. But if we add up, if we add like what our friend says here, add 2, 2 here, we will see that. We'll see what? Actually, the set becomes linearly dependent. Okay. Although these two don't have any linear dependent relation, right? Because we say that, because we already showed that there's no coefficient such that you multiply 1, 0 and 0, 1, you add up to 0, 0. But these three together form a linear dependent relation. Okay, non-trivial linear dependent relation. So we will say that this set is the set containing these three vector is linearly dependent. Okay, since 2, 2 equals to 2 times 1, 0 plus 2 times 0, 1. Although we know that the first two, I mean not just the first two, right? To pick any two of them, there should be linearly independent. Okay, can you try and show it? Pick any two of them, you'll see that they are linearly independent. Okay, but once you add them together, three of them together, they become linearly dependent. Okay, although any two of them are independent. Okay, yeah, try and show this. Okay, try and show this. Take any two of them. 1, 0, 0, 1 already show it. There's two more possibility, right? 1, 0, 2, 2 and 0, 1, 2, 2. Actually, you can quickly see from the pivot, right? Okay, if you look at it. So if you try and verify this sentence here, we are left with 1, 0, 2, 2 and 0, 1, 2, 2 here. So can you see that there are actually two pivot? There's pivot in every column here. Okay, there are pivot in every column. So if you try to do REF, right? Okay, maybe we quickly discuss. Let's do REF of this. What do you need to do next? You want to make the upper 2 to be 0. And so if you want to make this to be 0, you take R1 minus R2. So you get 1, 0, 0, 2. So you actually get 1, 1 after scaling. Similar for this one. The same, right? Can you see that they are equivalent, row equivalent? Can you see that these two are row equivalent? Because you can do row swapping. Yeah. Okay. Okay. So you can see from this picture here, right? This is a R3 picture here. So if you can see, say that they are linearly dependent in R3 case, actually they live on a plane because you write it as a linear combination of the two. I'm not sure you have seen this kind of picture in high school. W equals to U plus V, something like that. So it's a resultant factor. Is it what you learn? Resultant factor? Yeah. Okay. So if they are not linearly dependent or they are linearly independent, so let's say W is linearly independent to UV, meaning what? It doesn't live on the same plane. Okay, it doesn't live on the same plane. Okay. Or in other words, this plane here we call it span because we look at all the linear combination. So this plane in a mathematical term here, we call it a span. Remember last time I told you span was span out a space. So what kind of space? Either a line, okay, if it's span of one vector is a line. Span of two vector become a plane. Okay, span of three vector become a four vectors. Cannot draw it. Yeah, cannot draw it. Okay. Could be a hypercube. Cannot draw. All right. So here is the theorem. Okay, this is what I want to tell you here. So if T number of this vector here is greater than n, where is this n? This n refer to the where the vectors live. So where the vectors live, the vector should live in Rn. Okay, so if you have more vectors than the n you have, the dimension, okay, this is now I define as the dimension of Rn, then this set will be linearly dependent. Okay, this is what I have shown you just now. So there's only really one example I want you to keep in mind. So this one, so let's say you have R2, right? Okay, in this case you have R2, but you have more than two of them. Then there should be linearly dependent. Okay, we won't, we won't. Okay, we won't prove it. We won't prove it, but this is a very interesting fact here. Actually, not hard to prove, I guess, but a bit technical. But can you convince yourself with examples? Can you convince yourself with examples? Maybe for me, I'm very rebellion, right? Very rebellion. Do you know what is rebellion mean? Rebellion and rebellion on the rebellion, right? Very rebellious, rebellion. How to say funny? Huh? How to say? What? Rebel. Rebellion. Rebellion or rebellious? So maybe I will try more, right? Try more vector. Okay, try more vector to convince yourself that this is true. Okay. Yeah. Obviously, examples is not a way to prove it, but it's a way to convince you first. Okay. Mathematician is like this one. We have to convince ourselves first. So by convincing means what? We try to find why is it true. Okay, we look at a lot of examples. Oh, since all the examples have this property, so we must use this property. Okay, so we don't just prove by like guessing. We also do examples. Yeah, can you see that they are linearly independent here? Sorry, linearly dependent here. For example, 2, I already show you, right? 4, 5, 4, 5, how to make? Maybe 2 times 2, 2 plus 0, 1. Or you can make up 4, 5 using 1, 4, 1, 0, and 5 times 0, 1. There are actually more than one way to build, not just one way. There are more than one way to build. 1, 0, could be easy. Just use this one and this one. Okay. Yeah, so there might be more than one linearly dependent relation here. Okay, any question here so far? I think this theorem is pretty important. See it again in the dimension, I think. Yeah, we will make this n precise. What is this n here? You might be curious that, hey, why this n has such a significant role here? P is quite P is quite normal here because it's just number of factors here. But why has a relation with this n actually is quite interesting. Yeah. Okay. So later we will define this n properly. Any question? Other question? Before we jump to next part. So this part is about linearly independent. So later we will define dimension using span and linearly. We have these two ideas. And these two ideas is pretty important in linear algebra. Okay, if no question, let's go on. So there's a lot of examples here. Should we quickly do this example? Let's quickly do a. So this example asks you by inspection. Do you know what inspection means? What's inspection? Inspection means use your eyes. Check. Use your eye and check. Can you quickly check whether the given set is linearly dependent or independent? Maybe I give you 2 minutes. Try and do it. When the textbook asks you to do in inspection, usually the answer is easy to see. Okay, you don't need to go through very complicated calculation. Okay. Before we check the answer, do you have any guess whether they are linearly dependent or not? Not for all or which one? There are A, B, C, D, so 4 cases. Are they all linearly independent or what's your choice? Not dependent for all. Okay, you by inspection. Okay, so did you check? You checked. Okay, so what did you do? Can you tell us? Maybe choose one of them. Let's say which one? Which one you want to do? Let's pick one. Hmm? First one. Okay, first one. You claim that this is linearly what? Dependent or independent? Independent. Why? Can you tell us why? What do you do? So you set out the linearly dependent relation, right? Okay, you should show that. Show what? C1 up to C4 must be 0. Hmm? Right. Okay. But to solve these means what? You need to solve the augmented matrix. Okay, so what's the augmented matrix? 176, 209, 315, 418, and 00. Okay. Can you try and row reduce this? Sure. Okay. But if you row reduce this, right? At most, how many pivot you will get? 3. Okay. So you have a free variable here. Free variable means what? Your C4 can be random number. So it's not just the 0 solution. Okay. So meaning what? Actually, this is linearly dependent. Okay. But this also follows by this theorem here, right? Because the number of vectors already greater than the space, yeah, the dimension that your vector live in. Correct or not? Your vector live in are 3, but now you have 4 of them. Okay, either you can use this theorem to say that this is linearly dependent, or you can solve it and then you see that, oh, actually 0, 0, 0 is not the only solution. Okay, there's 2 ways. You can solve using the original definition, or you can use this theorem. Okay, in let's say in quiz or final, how do you quote this theorem here? Maybe you can say by theorem in the class. Okay, by theorem in the class, after by the theorem in the class, you need to tell me how you use this theorem. Okay, how you activate this theorem. Okay, how to activate this theorem. This theorem is a if-then statement. Okay, to activate this if-then statement, so you need the part after the then, right? So okay, let me set these. If so here got P, I don't want to use P again. So if S then T, I got S again. Is if what? If A and B, if A then B. Okay. So you need B. So meaning you need to tell me you have the A condition. Okay. Tell me that the number of vector is 4, which is greater than the 3. So by theorem in the class, we can say that this set is B and B. Yeah. Okay, cool. How about B? Okay. B actually is quite easy to see that. Is it quite easy? Yeah, quite easy to see that they are linearly dependent. Why? You cannot use theorem, right, in this case, because this vectors in R3 and then there's only 3 vectors here. But why is it linearly dependent? 0 vector. What happened to 0 vector here? You can multiply with any coefficient. Okay, not just 0. Still stand at 0. Does it make sense? Okay. So I think I need to produce you something, right? Let's see how I'm gonna produce you. So maybe we need to convince you. Let's see how to convince you. And so that's the statement here. If the set of vectors v1 up to vp and compare the zero vector, then it is linearly dependent. Why? Why is it true? Why is it true? How to show this? There's only one way to show something is linearly dependent, right? You set out the homogeneous linear system first, and then show that you have non-zero solution. And you have non-zero solution. So how to do it? Let's think about it. If you want me to think about it. How to find the non-zero solution? How to find non-zero solution? Okay, maybe we think of it using this case here. So can you set up? Okay, so again, and again. So let's move this away first. Let's discuss this, and then we can take a break from here. Okay, so let's discuss this. So C1 0 plus C2. Okay, so what's the non-zero solution you can take? C1, C2, C3. Right. So we can take C1 to be maybe 2. C2 and C3, we just kill it. Yeah, 0. Okay, sorry. Think something wrong with my good notes nowadays. Okay. Yeah, so we can kill C1, C3. But C1, we can put anything here because we already have a 0 vector. 0 vector will help me to take care of the 0. Okay. Yeah. How about C? I think C is linearly independent. Okay, so if you set out the augmented matrix here, I guess you should find 2 pivot. Yeah, go ahead and solve it. I think this is linearly independent. Try and check it. Independent. And then the last one I think is pretty easy to see, right? Linearly dependent. So you multiply by what? Negative 3/2 or negative 3/3. See which way you want to go. So let's say we do this way. So negative 2, 4, 6, 10 is equals to the negative 2 or 6. Okay. So you can see that if these two are linearly dependent, then they are really scalar multiple of each other. Or you can take the scalar to the other side, right? Then it's the same. Okay, any questions so far? If I go too fast, please slow me down by asking questions. Okay. Any question? Okay, if no question, let's break until 10:02.
如果你讲到那个东西是111的，那是 dependent or independent？
就
我
对，
就是这样啊。
对，因为你这个其实是 solve against 那个，对，因为你后面还有一排零，对不对？对不对？所以意思说 C 等于0 C2等于0 C3等于0，这样就有一个答案，就是 zero solution，然后就是0.0，除非你有多过000的答案。
对。
对，OK。 Yeah.
Can you enroll me in the course?
Oh, so who are you? Are you enrolled in the class already?
No, because I changed the
I mean, are you in the system or not?
yes,
In the SE system?
yes.
Yes. Can I check your name? Are you in the system yet?
Yes.
In this class?
Normally, yes.
What's your name?
Salami.
Maybe here. So what's your ID? Yeah?
SWE
FWE. Mm-hmm.
146.
Which year? Which year? Two. Which year?
Because yesterday I entered the course.
I mean, yesterday you entered the course.
Yes.
Why can't you enter the course?
Because I changed the
Okay, let's check here.
subject.
Let's check here. I just download SWE what?
146. 2409.
Okay, 2409. Okay. 126.
This is one. This one.
46.
Yes.
Yeah, let me see. Are you here now? Okay. Oh,
Because this is an old one
yeah, right.
from
Maybe someone swapped out because my number didn't change, but seems you changed. Correct or not?
yes,
So
because
meaning
I
maybe
added a drop subject.
yeah, maybe someone else also add a drop. So I need to add you in.
Because when I entered, there is a one place available.
When is it? When is it available? Yesterday.
Yesterday, yes.
Maybe someone dropped it.
Yes.
So you this one.
Yes.
Bellamy.
Salami, yes.
Where are you from?
Tunisia.
Where is it?
In the
Tunisia.
north of Africa.
I see.
Near Morocco and Algeria.
Okay. I think there are other two
Yes.
from north. You know them?
Yes, yes.
Oh, you know them. Okay. Good. Okay, thank you.
Can you
Oh, yeah,
enroll
right.
in
Sure.
because I want to
Definitely.
pass
Bellamy, right?
yes.
Okay, so I read this. Sure, I will let you in now. Every Friday. Yeah, every Friday. Quizzes.
30 minutes.
I think we will set it about 15 to 20 minutes like that. Yeah, we will set it not too long. It will be I will post the actual content to test, but usually it's previous week content. So for example, this week we learn chapter 1, then next week we'll test on chapter 1. Yeah. But I will post the detail again. So someone drop it, I need to remove.
Okay.
Okay.
Thank you so much.
Okay. I will try and check attendance for those who go to toilet. We can tell again later. 蔡美仪、杜佳伟、李雅涵、李延轩、翁佳命、郭书涵，OK，蒋生杰、天天、王月豪，OK，严子轩、青烧粉，OK，the front，天年耀，东宏卫，郭明洲，林凯俊，王依林，苏新宇，申博顺，然后 I think I saw him，蒋方林，阮秋子，黄 云溪，以指针，以指针，林心如，鸟心一样，千一气，千一气，千一气，后，说于姐，超之于，超之于，无生于，软弱起，哎，sorry，袁若起，袁若起，OK，李昌瑞，刘浩奇，赵宏哲，超之静，陈俊，Amber Lee，邱玉定，吴彦体，吴彦也是吴彦，Abdul Rahman，林思成，白嘉玲，韦嘉怡。嘉怡，Did you just come back? You just come back. Okay. 张月阳，张月阳，哭黄俊豪，黄俊豪 here or no? Okay. 雷乱，李坤，OK， 李坤，轩，Yeah， 萧亚轩，啊，蔡 B， 蔡 B 耶，蔡 B， Did you just come back or you were absent 2 days? What? Oh, you change? Huh? You change to the other one. You change back again. Oh. 百物城，葛文业，郭航宇，郭航宇，黄健，孙国东，张涵池，钟义阳，参台利，高子昭，吴瑞，金思浩，汉许，好，刘媛媛，鲁阳，蒙瑞阳，蒙瑞阳，汪宏明，汪宏明，吴浩瀚，吴一格，吴一格，吴一格，徐泽瑞，周，徐子周，赵泽宇，Abdel， Iba here 呢 ？Okay. Why are you so far today? You come here, okay. Benny, Yasmin. So are you absent 2 days ago? You just came back or what? I see, okay. Nori Mohammed. Like Sanai, I think Sanai. Huh? Oh, you changed place, okay. Sanai. Okay, Li Xuan. Chong Ziqi, okay. Edward, okay. 哈智慧，马一健，Shirin, not here, Shirin. Nicole, okay. Lim Zijun, Chu Hui, Ho Xing Dong. Okay. Anyone I haven't tagged your name yet? Haven't called you? Who have I called you? Okay, 你是谁？你什么号码
SW
？OK， 然后
409043。
很瑞的。 Anyone I haven't text your name? Yes. Eileen, what's your idea? What's your what's your code first? CME, and then what's your intake? 2404. Okay, one link. Okay. Okay, anyone else? Did I take your name? 问题 independent. Oh, yeah. So this one I need to write down, right? So sorry, I think a bit messy here. You can sit down. You can sit down. I can talk now. Oh. Yeah, I talk together. So okay, this part a bit messy. Sorry. So I will make a conclusion here, right? So since we got this solution here, so make it different color, easier to see. So this part is the set of vector is linearly dependent. Why is it dependent? Because you have non-zero solution. Okay. Yeah, you have non-zero solution. Obviously, if you put 0 here, still solve it, right? But the problem here is you have more than the 0 solution. Okay. Yeah. Randomly choose. Yeah, the point here is you can randomly choose. Not just randomly choose, you can choose non-zero one. Randomly, yes, randomly. Because why you can randomly do it? I mean, why is it enough to do it randomly? Because the definition here says that says what? Implies that the 0 is the only solution. So if you have more than 0 solution, then you are good. I mean, good to show that it is linearly dependent. Yeah, that exists, you see? Exists. Exists means you just need to find one that works. There could be more, but one is enough. Okay, any other question? Okay, if no, let's continue. Okay, next part. We'll look at function. Okay, so this is called a transformation, or you can see it as a function. Okay, both of them. So we will use transformation more than function here because we see these Rn as a space, in particular vector space. And for now, vector space for you mainly means that this space, the elements are vectors. Again, but later we will be more general. What is a vector space? So a function from Rn to Rm or transformation. So you can see that this n and m can be different. Again, not just Rn to Rm, can be different. So what's function? Have you guys learned function before? Function from x to y. And meaning what? I assign each vector in the Rn. So the first Rn. Okay, another vector called Tx in Rm here. So let's write it down. So T is a transformation from Rn to Rm. Okay, and then given you a vector in Rn, I need to give you a vector in Rm. Okay, so you see, so there's an idea of who comes first, who comes later. So the first one that comes, we call it domain. Okay, domain. So the first Rn, we call it domain. So this part here is a domain. And then where do we land? Where do we land? We land in a codomain. Okay. Domain and codomain. Does it make sense? Okay. So what does a function do here? For everything inside your domain, I give you one thing inside codomain. Only one thing. We cannot send it a different thing. Otherwise, we will say that this is not well defined. Okay, cannot one to many. Okay, it could be many to one. Okay, two different things get sent to the same thing. It's okay. Okay, but one can only go to one place. Correct or not? Okay. And then Tx here we will call the image of x. Okay, so this is where the x land in the codomain. So in this picture here, you have domain, codomain. Okay. So if you look at every element in your domain, it will get mapped into something in the codomain. And then this thing is called the image. An image of this X here. And this, if you collect all the images together, this is the range. Correct or not? So the range means this is where this T can hit. Okay, this is where the T can hit. Does that make sense? Okay. So you see, you have domain looks like this. Your range here must what? At most can reach this this size. Okay, at most you can reach this size. Okay, there could be a case that you send everything to the same place. You can do it. So for example, maybe this is one of the example. The other example was, let's say this is your domain, this is your codomain, right? You can just send everything, okay, to one point. Also can, okay, to one point. Then your range is just 1 point. And you can do it. So the at most you can get is this big inside your codomain. So that's why we create two words here, range and codomain. Okay, because your range might not be your exactly your codomain, but must be a subset. So later we'll discuss when codomain is equal to range, what happens. But usually it is a subset. Okay, you might not hit everything in your codomain. Does it make sense? Okay, because in this case, I can just map to 1 point. I can, every point I have 1 point enough. Okay. So the only thing you cannot do in a function is 1 point go to 2 point, cannot. Okay, this will cause us confusion. I don't know where to go. Okay, there's only one place you can go for each element. Okay, what's the next part? Right. So let's do some example, give you some idea here. So let's see. So now we want to understand the matrix vector here as a transformation. Okay, as a transformation. Why? Because if I define this transformation by, okay, so let me put here T from, let's say, R2 to R3. So meaning if you give me some vector in R2, you need to tell me, okay, you need to tell me what's the image of this guy here. Okay, what's the image of this guy? But the image of this guy live in where? Live in where? R3. R3 meaning what? You need to produce a vector in R3. So how should we call this? ABC maybe? Okay, you need to tell me an ABC. Give me a XY. How to do it? How do we do it? Okay, so in this case here, what do? We take what? We take a matrix. There's 3 times 2 size here. So let's call it a 3 times 2 size here. Okay. Multiply by xy. And I claim that this is a element is in R3. Does it make sense or not? Still remember this matrix vector multiplication? Still remember? What do? We need to split the matrix into column first. And then this xy is the coefficient for your vector. So can you see that this is actually a R3 vector here? Correct or not? Is this the R3 vector? Yes or no? Right, because you can use the vector, two vector operation such that you get x minus 3y, 3x plus 5y, and minus x plus 7y. Right, so this is the R3 element. Okay. Does it make sense? Okay, so this is the one way to get a transformation. Okay. So yeah, so I let you try first. Okay, let you try this 3 part, see what's the thing you can get. Yeah, try and work out this. I give you 2 minutes. You can try and discuss with your friend. And maybe you need to refer to the definition again. And then we can discuss. Try discuss with your friend. Yeah, introduce yourself to your friend beside you. Ask them. Okay, check answer. I think there's a REF involved. Maybe give you a bit more time here. Yeah, please practice doing these in class because so you're gonna get quizzes, so you need to get used to doing calculating in class. Okay. I give you 1 more minute to try. It's okay to get start. Get start meaning you are trying. Okay, so in class you get start is fine because I can help you because we can discuss. We got answer. All right. Let's see if we got the same answer or not. So for the first case here, okay, A is given. U is also given. Okay, so you want to calculate the specific U here. So TU bar here. But how this TU is defined? Okay, so it's defined by AU. Okay, so what is A? 1, 3, -1, -3, 5, 7. And what is U here? U is given by 2, -1. Okay, so this is a matrix vector product. Okay, so you need to recognize, okay, recognize this. This is called matrix vector. Matrix vector product here. How do you do it? You split your matrix into column. Okay, and then you multiply by the coefficient using the factor. And then you add them up. What's the answer? You want to calculate. 5, 1, minus 9. Okay, did everyone get this? 5, 1, minus 9. Okay, good. So this is what? This is the image of U. Okay, can you see the significance of this or not? You go from R2 space and become a R3 space. Okay. Number generate 3 numbers. Okay, no? So this is a nice thing about transformation here. And then did we done with A? Yeah, we done with A. How about B? B says what? Find an X R2 whose image under T is B. So find X such that AX equals to B. Okay. And then ask you, whether there are more than one such x or not. Okay, let's see. So A is given 1, 3 minus 1 minus 3, 5, 7. X you want to find, right? So X live in where? R2 or R3? Domain or codomain? Sorry? Domain. Right, domain, right? AX, right? So this part here. So this guy live in domain. Okay, so there's only two spots for it. X1 and X2. B, what is B? B is a vector in R3 here. So minus, so 3, 2, minus 5. 3. So see, again, we want to solve this. This is what? Linear system. Right or not? Okay, so to solve it, you can use what? Augmented matrix. So it is equivalent to the augmented matrix. Okay. So should we do it? Let's do it. So R2 minus 3 R1 and R3 plus R1. Again, I want to warn you, if you want to do multiple row, make sure you don't do on the same row more than once. So we get this 0, 6 plus 9. 9 becomes 14. It's 9, 2 minus 9 minus 7. 0, 4, 2. Right. This one minus 2. Okay, and what? So I think it's better for us to scale it. So let's say we scale both row again. You can try and calculate together, or you have finished. Oh, you see very nice thing happening here. The two equal rows here. So you can take R3 minus R2. Okay, so it's not raw reduced form because we want to get the solution out. It's better for us to get to raw reduced form. Some of you ask me, can we stop here and then go and do the substitution? In principle, you can. In principle, you can. But I think we can do the raw reduced form directly. Okay, actually, it's similar. It's more convenient, actually. Okay, the whole point we introduce augmented matrix is because it's more convenient than doing substitution. You don't need to write the variable anymore. Okay, otherwise you do half. Can, in principle can, but you go back to old style. Can. So you get 1, 0. And then what did you get for the third term here? 3 plus 3 minus 3 over 2. So you get 3 over 2. Okay, good. Okay, so what did you solve here? Your x1 have to be 3 over 2. Your x2 have to be minus half. So up to this stage, right, you should do what? It's better that you go and do your sanity check. Put it back. Okay, maybe you have some error in doing ERO here. Okay, the raw reducing step. So make sure you go back and check. Check what? Check whether you really get the right matrix equation or not. Okay, go and check. Please check. Please check. So please check this. Okay, maybe you might have some calculation error. Okay, so once you check this, for sure you know it's correct. So the next part of the question says what? Is there more than one such x or not? Is there more than one such x? Is there more than one such x? What does this solution tell you? This is the only solution. If there's more than one such x, what happened? Can you guess what happened? What could happen if there's more such x? you will have a free variable. Yes, you will have a free variable. Okay. Because why is it free? Because you are free to choose any number such that it works. Okay, so in this case here, already fixed already. X1 only one choice, X2 only two choice, and these two choice make up only one choice. Yeah, unless you have free variable, very good. So how do I write it? There's only one unique X that works. Okay, unless there's free variable in your solution. Come on. Any question? Okay. Okay, last part. Determine whether C is in the range of T or not. Determine C whether it's the range of C. So do you recognize that actually B and C is the same question? Just use different language to ask you. So C says what? Whether T can hit C or not. T can hit C means what? There exists an element in your domain such that AX equal to C. Okay, it's the same question actually. Okay, it's the same question. So anyone calculated? Did anyone calculated? So maybe I quickly give the calculation, not calculation, but the result. So again, it's the same question. So you want to solve the augmented matrix, but this time it's not B, it's C already. Okay, so if you quickly solve this, you will get this REF here. Okay, so if you see this REF, what can you conclude? This linear system is inconsistent. Why? Because the last line you have a contradiction. 0 equals to 10. Okay. For the associated linear system is inconsistent because 0 is not equals to 10. Okay, so no. Okay, there's no x. So there's no x such that x equals to c. Okay, so try and work out yourself. Try your own. Okay, so I will split these calculation into two parts. One part is whether you know how to do row reduction or not. The last part is whether you know how to read the solution or not. Okay, so we split the skill into two parts. One part you need to know how to do row reduction. The other part you need to know how to read solution. Okay, basically it's these two parts. Throughout these 3 days, okay, we are keep doing this. Use different language, whether span, linearly independent, okay. Now transformation, image, range, okay. But all of them are using the same calculation. Right. Okay, so far. Any question? Any question? Or did I did my answer wrong? You also can check. Okay, next. All right, next. Next, we will talk about a specific transformation here. Okay, so there's a specific transformation we'll do here. So this is called a linear transformation. You see, whatever you did in a linear algebra, all the words will have an adjective of linear also. Okay, independent, linear independent. Right. So here transformation, we want a linear transformation. So what sort of transformation is linear? Okay, so let's see. What sort of transformation is linear here? So let's say this is transformation from Rm to Rm. Is linear if what? If first part, if T of u plus v equals to Tu plus Tv. So meaning what? You can split, okay, split the vector sum. Okay? If you want to compute linear transformation on the sum of vector, actually you can compute on each of them first and then add them up. Okay, you can bring the sum up. Or if you want to compute linear transformation on a scalar multiple, you can really check it on U first and then scale it. Okay, so meaning what? You can pull the scalar out, or you can pull the summation out. Okay, so there's one thing I want to share to you here. So let me draw something here. So this part A here, we will say that T will respect vector addition. Okay, respect vector addition. So what's the other way to see this? So let's put our domain and a codomain here. Okay, actually this equation here really describe two paths. Yeah, describe two paths here. So let's take U and V out from your domain. Okay, what's the first thing you can do? You can apply T first. Okay, so such that you get TU and TV. Or you can add them together first. Okay, such that you get TU plus TV. Okay, so here is addition. On the other route, you can also add TU and TV, right? Okay, TU and TV together. And potentially you can map this TU plus V across also. But the point of a linear T, these two things have to be coincide, or they have to coincide. Okay, yeah. So actually, TU plus V and TU plus TV are two ways to reach Rm. But when T is linear, these two things have to be equal. Does it make sense? Okay. Similarly, you can do it for CU here. Okay, so we will say that this TCU equals to CTU. We call it respect scalar multiplication. So it respects scalar multiplication. Okay, so actually this is also two ways to get to your domain. So one way is to do the so should I do it on the same picture, or maybe I do it on the other picture? Okay, let's do it on the other picture. So so B, part B. So what can we do? Let me show you something. So, okay, maybe let's not draw the space out first. So what do? We quickly draw it. So we have C and V together, okay? One way is you can multiply them together first, okay? And then the other way is you can map them across, okay? So if you map them across, so you have T here, okay? And what? You also have C here. Okay, keep the C. C, you did nothing to C, basically. And or you can multiply C and TV together. And then on the other side, what can you do? You actually can send the whole CV to the other side. But when T is linear, they coincide. Okay, so two ways are so one idea I want you to think about is whenever we put something equal to something, right? So you should think about left and right potentially come from a different space. Different way, not space, different way. But they coincide, they equal. For example, y equals to x, right? Y and x actually not equal. Correct or not? Y and x not equal. But x is equal to x, correct or not? But y and x is not equal. But when are they equal? This is the problem of linear algebra. So whenever you see equal signs, right, on the left side, on the right side, potentially they come from a different way. They come in different way. But we want them to be equal. Or when are they equal? This is our question. Okay? Yeah. So be careful when you see equal signs every time. Correct or not? Account, right? Account. Does account count in different way or not? I'm not sure. Do you get the same number from different way, like for account student, or do you just get the final figure one way? I don't know. Maybe auditor can change the way to calculate it. Correct or not? I don't know. But try to be as honest as possible. Okay. So why we talk about this linear transformation here? So one theorem is matrix transformation, linear transformation. So what's this matrix transformation? This is exactly what we did just now. So you have Tx defined as some matrix times A. So this is called the matrix transformation. These are linear. Okay, these are linear. So meaning what? You need to check that. So check that A times X plus Y equals to AX plus AY, and you check that A times CX is equal to C times AX. Okay, you need to check this. Okay. Okay. So basically, how to check this? You need to spell out every term and then do the matrix vector multiplication. Okay. It's not too hard to check, but I don't think you need to worry too much for this part for exam. But if you are interested, you should prove it because it's an easy proof here. I think I showed you the R2 case last time, right? R2 cases with two number only. But in general, it's also true for Rn. Rn to Rm. Okay. Can you imagine or not? At least imagine. If you cannot write, at least you can imagine it. Okay, so if you have two vectors here, you can add them out into one vectors, right? And then you do the matrix multiplication. Okay, and then you split it up. Or you multiply C to every term in your vector first, and then you do the matrix multiplication, and then you pull out the C. Yeah, because why? Because when you multiply together, what's this? This is another vector. But you can see that in all the terms inside this vector here, you got a C. So you can pull the C out. Okay. Yeah. Try and write it out. Try and write it out. If you're still confused, right? Try an example. Maybe try an example. So maybe try this example. Maybe. Okay, maybe try this kind of example to see it. Anything you can try out. Yeah. Yeah. Try a few examples. Then you can see. Okay. Okay. Next is if T is a linear transformation, T sends 0 to 0. Okay, since T sends 0 to 0. Actually pretty fast, pretty easy to prove here. Maybe I just quickly show you how nice is it. 0 might not go to 0, right? Right, might not go to 0. But if it is linear, it have to go to 0. So how do we do this? So let me show you a very nice proof here. So let's write 0 as some vector minus x. Okay. And then obviously I can apply linear transformation to both. Okay. But what can I do on the left-hand side here? Sorry, right-hand side here. I can split the sum. Okay, because this is really T of V plus minus V. Yes, correct. So I can put it as T of minus V plus T on minus V. Okay. But remember that last time, what did I told you? This minus V is what? Actually minus 1 times V. This is also what you learn in high school, right? You can pull the negative out. Okay, it's similar, but not rigorous. But now I'm going to use it. And I can pull it out minus 1, right? Because linear transformation respect scalar multiplication. So I can pull the negative 1 out. But again, what is negative 1 times negative V here? It is just the inverse of EV, which is 0. Okay, yeah. So it's a very nice proof here. So why this proof is nice? I never write down the T. I didn't write explicit. I didn't define T here. I just use the property of linearity. Okay. And also the property of vector. That's all. So nice. Okay. So linear transformation have this nice property. And next up is if you gonna add on a finite linear combination of vectors, you can split all the scalar and sum out. Why is this important? Because I just only tell you how to split two, but in fact you can split more. Okay. This have to use induction to prove, but you can accept it. Okay. Okay, so you not only can split two of them, okay, you just not only can split two of them, you can split all of them, actually. Okay. So a main takeaway here is you need to know how your T add on some specific vector. Once you know how to add on those specific vectors here, then you will know how to add on the other vectors. So, okay, another way to think about this is if you know T how T acts on this V2, V1, V2 up to Vp, right? You know how T acts on the linear combination of V1 to Vp. Does it make sense? You get what I mean? So let's say I don't tell you how to add on this particular vector here, but I know the T how T add on V1, V2, Vp. I would know how T add on they are linearly combined. Any question? Do you understand what I say? Any question? If you don't understand, please ask. I don't expect you to know directly because obviously you first learn this. Okay, so maybe I just repeat one last time before we go to the next one. So as long as we know how Tx on these Vi, we will know how Tx on their linear combination. Okay, how? By this equal sign here. Okay. Any question? No. Question? Okay, maybe I test you. I need to test you. So maybe I test you. So let's say, okay, maybe I test you. So T, let's say I know how T add on 1, 0, which is maybe 2, 0. And then T is acting on 0, 1, which is 0, 2, same. Okay, so I ask you a question. How T acts on 2, 2? Yeah, can you figure out this? So let's say I define these two. Oh, no battery. Okay, so can you figure out this using part B? Let you think for 1 minute. If I have this definition, can you use part B to figure out where this 2, 2 have to go? Yeah. So you should write your 2, 2 as a linear combination of 1, 0 and 0, 1 first. Okay. And then use this theorem here says what? To compute T on this linear combination, you just split everything out, right? 2 times T of 1, 0 plus 2 times T of 0, 1. Yeah. But I already tell you what happens to 1, 0 and 0, 1, right? So let's move this. Oh, I already told you that 1 0 will go to 1 0 will go to 2 0, and then 0 1 will go to 0 2. So in the end, you get 4 4. Okay. So this part here is by part B. Question? Okay. So you can see that to solve this, you really need to know how to do the linear combination. But how to find this 2, 2 here? You use the augmented matrix if you want to use it. Otherwise, in this case, it's easier. You use inspection. Yeah, in usual case, you use the augmented matrix row reduction. Okay, any questions so far? Question? Any question? Henry from the front. Yeah. You mean this line to this line? Okay, yeah. So what happened? Oh, this is what I defined just now. Yeah. Yeah, this is what I defined. So whenever I put this dot dot equal, dot dot equal is defined. Okay. Any question? Other question? Okay. Right. How about this one? Let's see. Let's look at the few examples of linear transformation before we take a break. So describe the linear transformation x to ax, so given by 1 0 0 0 1 0 0. Okay. So well, I give you this this is a matrix transformation, right? So matrix transformation is linear, which is what we showed just now. Can you identify what spaces we are going through? What's the domain and codomain here? You want to guess or think about it? What kind of vector to put here to make sense of the matrix vector product? How many coefficient you need? How many columns here? 3, right? Okay, so you should put 3. Otherwise, the matrix vector product doesn't make sense. Okay, because there are 3 columns here, you need 3 coefficient. Okay. But what did you get out of that? What do you think? If you have let's say 1 0 0 0 1 0 0 0 0 multiplied by x1, x2, x3, what do you get? What space you live in? Sorry? Cannot hear. Someone say something. What did you get here? So what did you get? By definition, what did you get? X1 times 1 0 0 plus x2 times 0 1 0 plus x3 times 0 0 0. So in the end, what do you get? You also get R3. Okay, you also get R3. Okay, so whenever I gave you a transformation, right, make sure you know how to figure out the problem. But in this case, did you notice something? If you add this 3 vector together, what's the end product here? What's the end product here? Can you compute? What's the end product here? Can you tell me the 3 entry in your vector? X1, X2, and 0. What happens? Can you see what happened? I input S1, S2, S3. Suddenly S3 become 0. What does this mean? S3 usually represent the Z variable, is the height. So your height become what? 0. Okay, your height disappeared. So meaning in this picture here, what you do is you project all your point onto the Z equals 0 plane or S3 equals 0 plane. Okay. Project to this X3 equals 0 plane. They are on the same height. The height is S3 equals 0. Okay. Does it make sense? Okay. Yeah. So all these points get project to this X equals 0 plane. Okay. All right. How about next one? Describe the linear transformation X to AX where A is RR0. So what do you think? What's the domain for this matrix here? R what? R2. Okay. So if you compute this A on R2, what did you get? R what? Still R2. Okay, still R2. So let's say if I put a random X1, X2 here, okay, and then I multiply by R00R, what do I get? I get R X1 and R X2. In other words, what does it mean? I'm scaling my vector here. Okay, so depend on what R you put, either if R is greater than 1, it will make it longer. If R equals to 1, it's just identity. If R is less than 1, you will make it shorter. Okay? Does it make sense? Okay, no? So R greater than 1, increase the length. R equals 1, length remain. And then R less than 1 reduces the length. Okay? All right, how about the next one? 1301. Okay, so this is a map from where to where? Again, R2 to R2, right? Because there's only 2 columns here. And then you can notice that actually what? Actually, the size of your codomain is determined by the number of rows you have. Correct or not? So if you have 1301 here, you need 2 coefficients, right? So meaning you need x1, x2 here. But what you produce here, what's the vector you produce here? Actually, it's the number of row you have. Correct or not? Okay, so the size of your domain is controlled by the number of columns because you and then the size of your codomain here is decided by the number of rows you have. Because this is the size you're going to. If you try this, what happens is you do a shear. Okay, they call it a shear. You kind of elongate the shape on the other way. Okay, they call it a shear here. So this is a shear transformation. How about next one? How about this one? Okay, so this is also a map from R2 to R2. And what happened if you inject a random R2 into it? So let's check on random R2 vector here. What do I get is minus x2, x1. Okay. You know how to compute this? This is x1 times 0, 1 plus x2 times negative 0. Okay. So what happens? X1 and x2 swap. Not just swap. X2 have a negative sign. If you try and plot a few points out, actually it's a rotation. It's a rotation. Okay. And what this rotation is, it is a counterclockwise by 90 degree. Okay. So how to easily see this? Maybe you can try the easy vector first. For example, what's this vector? 1, 0. Okay, you can see what happens to 1, 0. What happened to 1, 0? Becomes 0, 0, 1. So where is 0, 1, 0, 1 here? Okay, at the top. And then you can see where does 0, 1 go? Negative 1, 0. Where is negative 1, 0? Again, 90-degree swap. Okay, yeah, so you can check on this simple vector first. Okay, these are the simple vector. Instead of checking that hard picture there. Okay, check on this simple picture. So you can see that 1, 0 gets sent to 0, 1. Maybe use the other color. And then 0, 1 gets sent to negative 1, 0. Okay. So more generally, this is the rotation matrix here. Okay, more general is this one. You can see that if you put theta equals to 90 degrees, you will get this. Right or not? Sine cos 90 is what? Cos 90 will 0, right? Cos 90 is 0, sine 90 is 1. So that's why you get that. So more general case is this. So this one you can do random degree counterclockwise. So when theta is 90, it reduces to that simple matrix. Okay, so if you want to see more, right, there's a lot of nice picture inside your textbook. Let me see. There are nice picture inside your textbook. Yeah, so there are nice picture inside your textbook. You can have a look. Okay, what kind of matrix? How to transform a picture inside your R2 space. Okay, the direction of this fish is pretty important. You can see that in some cases, the ship, the orientation of this fish changes. Okay, sometimes it doesn't change, sometimes it changes. So you need to be alert. Not just the size of the fish can change, but the orientation also can change. Orientation. Yeah, so there are examples inside your textbook. Okay. Any question about linear transformation so far? Any question? So within this hour, what I want you to know is matrix vector product is a matrix transformation. In particular, it is linear. Okay, what does it mean by linear? Linear means what? Two things only. Respect vector addition, respect scalar multiplication. Okay. Yeah. In the next hour, we will learn that any linear transformation between Rn and Rm is a matrix transformation. So this is nice. Why is it nice? Any kind of transformation that respect vector addition and scalar multiplication between Rm, Rn, you can write it as a matrix vector multiplication. So this is nice. So you can turn the question back to your linear system again. Okay, we will look at it in next hour. So let's break until 11:07. Yeah.
你要讲一个 consistent 硬 persistent 的这种，基础的就是来好吧，这边是来零啊
OK，
这边是来零不对五嘛，
对，
这个 consistent 如果有 free variable 是有 consistent 的，还是有
free variable
不是有 solution
对呀，有对呀，
什么情况才是 no solution？就是
就这样吧。
就这样吧。
我想一下，应该是就这样吧，因为为什么没有 solution？ 是因为什么它没有
为
solution？
什么这样是没有 solution？其实零
等一下，you want what system? What do you want? Oh, okay, so okay, sure.
因为零不等于是零，它是都是
对，没错。 你是说为什么这个会代表它没有答案？
啊，对，
有想想啊。我可以建议你做一件事情，你给我比一下。我可以建议你做一件事情，比如说我们不要看这样复杂啦，看更简单一点啦，maybe 看这个啦就好了。可能你可以问我这个东西从哪里来。
equation
I mean, OK，如果这个直接读出来的话是这样子嘛，OK，这样就很没有意义嘛。Obviously，我知道了，零不等于3，但是你要记得，我们这个东西有可能是从一个地方 raw reduce 出来的。OK，比如说我们有一个情况是 y 等于 x 跟 y 等于 s 加1，我已经告诉你这个已经没有 solution 了。但是你看零等于，I mean，给我想一下啊。OK，对，我觉得这个很好了。所以这个太夸张了，现实生活中一看就知道不对啊。但是问题是我们每次算到这个是从 raw reduce action 分来，所以假设这个情况，我1减1 0跟100，1减1 1，够吗？是翻了。
减
因为我翻这个1，翻这个1，对，减1，这个 OK。但是啊，这一个啊会 raw reduce 成什么？raw reduce 是什么？1减1 0， 0 0减1，所以这个这么夸张的东西是从哪里来的？讲一下，我们从哪里来 ？raw reduce， 你在做 raw reduce 的时候，其实你在这边也是在做一个 algebra 的，所以你到底做了什么事情？其实，OK， 简单来讲是我们两边拿来减的，但是这个是什么意义来的？
那两边的那一减两边的差的一样。
这个意义是这个，就是我知道 y 等于 x， 然后我再把这个 x 上进来，然后你这个 raw reduction 的意思其实是你把这个 x cancel 掉，懂吗？你减 x 在 both side， 所以你才会拿到0等于1。所以你从这里可以理解来为什么没有答案吗？
x 不等于 x 加1
对，没有错。其实重点是这个，其实，但是怎么看到这个，其实就是可以 reduce 去这个，但是确实你讲的对 ，x 不可能 x 加，在号码世界里面，对，没有错。
抽象了，
抽象咩？
抽象。
为什么？不是很 concrete 咩？真的看到这个。
讲用 graph 啊，
graph 可以，但是 graph 因为我们也是 sketch， 所以也是有一点不太准啊。但是就是为什么呢？因为它的 OK， 第一它的 y intercept 不一样，第二它的那个也对加对没有错。对，这里我是觉得这里蛮抽象的，这里我觉得就很那个，这里也是蛮抽象一下。但是你要记得你自己在做这些东西的时候，其实你就是在做这种东西。
OK，在想
Yes.
To make sure that it might absent because I kind of changed the subject.
Oh, okay.
It's still open, like.
I think that's fine. I think if that's I think first week still fine because like you said, people like swap in here, swap in there.
Like there.
Yeah.
So
Sure.
we're good.
Sure.
Okay.
Yeah, sure.
讲这个是 linear dependent，
对，没错。
这个就是可以
那你 try 哦，你就 try 哦，你看一下有没有符合这个条件。你看你的 n 是什么？你 n 是4哦，你的 p 呢是2，所以2小于4，不能够用这个条件。
所以这个条件不是每次都可以用。
Yes， 你一定要符合这个 p， 符合前面一个 part。if 的这个符合了 then 才会发生，不符合就没有关系。
这几个例子，
耶，
那我们的 solution 是怎么写？就是全是用 x 吗？
暂时是这样子，对。
哦，不用代入。
其实他 describe 的意思，我觉得应该是他要不用，因为你为什么？因为你要解释所有的点发生什么事情。其实他要你解释应该是这些图了。对。但是我们怎么找到这些图是用
这怎么解释？
这个怎么解释啊？
说这个怎么？
对，这个确实是有一点难说，因为我现在还没有告诉你长度怎么算嘛，对不对？
哦
但是就是我给你的一个概念就是 scalar 一乘上 vector 就是长度的改变，这是我直接告诉你的，因为我们还没有具体说。
因为我现在还不知道到底具体 describe 这些什么。
但是你只能够跟着这种情况，就是给这种图片，对。
然后知道它是大概这样子
对对对对，
变换。
检查某一条线，然后你去看到对那种，
linear transformation 它到底是什么意思？就是这个
就是符合这个两个条件就可以了。
就叫做 linear
对，没错
transformation。
对，就这两个。
怎么通俗的理解？就怎么
通俗就是我告诉你的那两条路咯，那两条路这两条路，对，这两条路是分开的路了，但是只有 linear 的情况下他们会的。因为这两个 ，OK， 等一下我说，等一下我说。哦，怎么确定？哦，对对对，OK，第一就是你看啊，如果你要做 matrix vector multiplication 呢，你要怎么来 make sense of 那个 product？因为这里有两个 column 嘛，还记得吗？我们乘的时候我们要把它 split 成 column 嘛，所以有两个 column 所以有两个 column 你就需要两个 coefficient 咯，对不对？所以你的 domain 就要 R2咯。但是这一个怎么确定呢？你要从这里算得出来的东西来确定哦。但是你要想想看，你这里的 vector 是活在哪里？活在 R2里，所以你加出来的 vector 一定是活在 R2里，所以
那这个就是根据
那我
这个
这样子写
来确定的，对不对？
对，你等一下啊，我写一个完整的句子出来。其实我应该要写出来比较好。这个 A 呢，一定是 A 一 A up to A 一。对，这样的话你才可以配得上 A 一 A。S2 到 Xn，因为有 n 个 column，然后你得出来的东西只会有 y1 y，m， 对，因为它的 number of， 所以要怎么说啊 ？OK， 说这个 n 是 number of columns。
可以，
可以
理解。可以，还有一个这个，这个
，yes，
就是这个就只能通过看一眼发现。
不，看一眼是你就是猜先，但是要真正证明的话，像我讲的，你就 row reduce
row reduce 它
过后，它的 solution 只有0，因为你要证明 linearly independent，你一定要证明说这一个的解是00，对不对？所以你要去解那个，就是要回去我们的 matrix 对，它的那个 coefficient 可以是一样的。
这两个
这样看，但是看你可能你是说可以嘛，但是现在问题是要证明啊。
它好像可以。
怎么说？哪一个？用哪个？怎么证呢？你怎么证呢？因为你要用这一个的话，你要证明它不是 multiple of each other 嘛，不是 multiple of each other，不是就是在整体证明那个 coefficient 是00了所以你要证明那个 coefficient 00，其中一个方法就是用那个 augmented matrix
下边对。
因为如果证明它是 multiple，你只要去找那个 scalar 出来， 但是如果要证明不是的话，你要说所有的号码都不能够问，所有号码不能问，最简单的方法就是这个 momentum equation。
目测的话可以像这个一样，
可以啊
它，是有倍数关系。
对
这个没有倍数关系，那可以目测出来它就是谁呢？
就是说我是说你要怎样证明
证明
没有，对不对？
嗯
证明有就找一个嘛，证明没有呢，
除了那个
你要所有以外都说不可以嘛，是不是啊？是不是？对，可以，谢谢。Okay, before we go to next part, one thing I want to remind you is, given you a matrix, how to decide what is the codomain and domain here. So basically, your domain Rn is controlled by the number of column of A. Okay, controlled by the number of column of A. Because for this matrix vector product to make sense, you need to split your matrix into columns, right? Okay, and then you count how many coefficient you need. So this is basically the number of columns of it. And then what did you produce? What did you produce here? Where do you get this M here? This M actually is the number of row of your A. Because after you split your columns, okay, split your matrix into columns, what is the size of your vector? The size of your vector exactly is the number of row here. Okay, or not? So the M here is controlled by the number of row of A. Okay. Okay. The other thing is people ask me how to intuitively think about linear transformation here. How to think about linear transformation here? Really, linear transformation, just these two property here. T have to respect these two property. Did you notice that this two property is the only operation you can take on vectors? There's only two things you can do on vectors. You can add two vectors together, or you can multiply vectors by scalar. And this linear respect both operations. Okay, that's all. Yeah, no? Yeah. So this is the two operations that you can fit in your vector space. Okay, in your R. So it respects it. So meaning what? You can either do the sum first or do the sum later. Doesn't matter. Okay, they're still the same. Okay, you can do it first or do it later. Correct or not? I show you the two path, right? Okay, where's the two path? Yeah, the two path, right? You can add them first and then go to the image, or you can go to the image. They are the same. Okay, so this is what we call respect. Right? I respect you, man. I didn't change you. Correct or not? Didn't change. Okay, although we use a different way to do it, the result doesn't change. Okay, two ways get the same. Okay, so this two property here is quite important. Why? Because this is the only two things we define for a vector. Vector addition and scalar multiplication. Okay, no? Okay, right. Let's see. Okay, let's continue first and then about it. So now the topic is the matrix of a linear transformation. So just now I tell you that. Should I do this first? Okay, back out a bit. I want to do some logic thing before we continue because we're gonna meet a lot of this kind of logic. So let's say if P then Q. Okay, so to get Q true, okay, we need P true. Okay, let's say P is false. Say P false. Can you say anything about Q or not? Cannot. Okay, this statement says nothing. The theorem says nothing, 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 nothing about Q. Okay, Instead, you need to look for a statement like if not P, then Q, or if not P, then not Q, something like that. Okay. So if the theorems only go one way, you can only have P implies Q. You have P, then only you have Q. Okay. If instead you have not P, I mean P is false, then you don't know what happened to Q unless you have a new statement here. Unless you have new statement. If not P, then Q, or if not P, then not Q. Unless you have another connection. Otherwise, you say nothing. You don't know anything about it. Okay. But one thing you could know is if P then Q is also equivalent to if not Q, then not P. Okay. For example, if today is gonna rain, then I'm gonna bring an umbrella. If I don't bring an umbrella, that means today doesn't rain. Cannot. Okay. But if today rain, either I could bring an umbrella or didn't bring an umbrella. Okay, so this is some logic you need to be aware of. So if there's only one direction, then there's only one direction. Okay. This direction you can go backward, but if you go backward, you need to put not on both sides. Yeah. Otherwise, you need to look for a new connection. Okay, so this is pretty important statement. I think this is quite how to say quite useful in real life. Okay, sometimes when you listen to what people tells you, you need to stay in the right logic. Otherwise, you will confuse yourself. Okay, continue. So in the last hour, we say that every matrix transformation is a linear transformation. But now we're gonna build matrix for every linear transformation. Go backward. Okay, so we want to go from linear transformation to matrix transformation. Okay, so just now we have a matrix transformation. The matrix vector product is a linear transformation. Okay, so now we're gonna go backward here. So we're gonna go backward. Okay, so we're gonna go backward. Or matrix of a linear transformation. If I gave you a linear transformation, you can write it as a matrix. So for example, in this example here, TR2 go to TR3 is a linear transformation such that they only tell you how this function or linear transformation add on these two. Okay, these two vectors here. In fact, it is enough to tell you how we add on 1, 0 and 0, 1. You can know what happened to all R2. Why? Why? So for any x in R2, right? How do we write this x? X is equal to what? Let's say x1, x2, right? Okay, for some x1, x2 in R. Okay, so the question is, how do we figure out T of x1, x2? Still remember? What's the connection between x1, x2 and 1, 0, 0, 1? What's the connection? Sorry? What's the connection? What's the keyword here? Linear combination. Okay, can you write x1, x2 here as a linear combination of 1, 0, 0, 1? X1 times 1, 0 plus x2 times 0, 1. Okay, but remember that what did we say about linear transformation just now? When T add on the sum, okay, when T add on the sum, we can split the sum out. right? T respect vector addition, right? And when T add on a scalar multiple, you can bring the scalar out. Respect the scalar multiplication. Okay. But what is this? Yeah. Okay, but what happens now? We know what Tx on 1, 0. We know what Tx on 0, 1. Okay, so what are these? X1 on 5 minus 7, 2 plus what? 2 minus 3, 8, 0. Okay. So what did you get? So what did you get? So you can write it as 5. Okay. So write it as 5. Wait. 5x1 minus 3x2 minus 7x1 plus 8x2 and then 2x1. Okay. Okay. But can you write it as a of x bar or not? Can you find the a? Can you cook out a matrix vector right here? The matrix you should take here. A equals to what? 5. Okay, 5, negative 7, 2, and 3, negative 3, 8. Okay, so this is the matrix product, matrix vector product that we talked about last time. So this part here is the matrix. Okay. Okay or not? So the solution can stop here. Stop where? Stop here, yeah. Okay, can stop here. And then what I want to show you is Tx can also be written as a matrix. So solution can stop here. And this is here. Okay, you can express your linear transformation as a matrix. Okay. Okay, so actually this is very special. This is very special. Why you can do this? Because this is a clever choice of this guy. 1, 0, and 0, 1. Okay. This is what we call a standard basis. Okay, standard basis in R2. Okay, standard basis in R2. So in Rn, right, you can consider this n possibility here. So what's this n possibility here? This is like the, if you notice, this is like pivot column. Pivot column in different spot. Okay, there are n spot here. Okay, so they form what we call a standard basis. Later, we will justify why we call it a standard basis. In the dimension chapter, okay, we call it a standard basis. Okay, so basis is like a base, right? So they are kind of a base of our. Oh, does it look like pivot column? What does pivot column have to do? You have a pivot position, and then below this pivot position is 0. And then inside the REF, you should make everything above this pivot position to be 0 as well. Okay. Yeah. Okay, so this guy is very important. Why is it important? This guy will help you to find the matrix. Okay, this guy will help you to find the matrix of your linear transformation. So this is a theorem here. So if you have a linear transformation from Rn to Rm, you can try and find the matrix that represents this T. So how do you find it? You basically again split this matrix into column. And then who makes out this column here? You just take your linear transformation, add on those standard basis. Okay. Let's look at the example before. Look at this example. You see, this linear transformation, we are trying to find the matrix that associate to this transformation. Okay, so let's copy this down. Is here. Okay, so let's say we want to find the A that describes this T here. So by this theorem, right, what this theorem tells you is you let A add on TE1 and TE2. Okay, so you see this N here follows the size or the dimension of your domain. So your domain is 2, so you have only E1 and E2. Okay, but how big is your E1 and E2? Huh? How big is your E1 and E2? Okay, how big is your E1 and E2? So what is this standard basis here? This EI here, this I here correspond to where you put the 1. Okay, which row you. Okay, so if it's E1, you put the 1 at first row. If it's E2, you put the 1 at second row. And then EI, you put at the ith row. Okay, so in this case here, this E1, E2 here. So E1 has what? Has 1 in the first row. Okay, and then E2 has 1 in the second row. Okay, but these two values are defined by your linear transformation. So you just put it in as your column. Okay, and this is the matrix that we compute just now, right? Okay, using the matrix vector product. Okay, no? So how it works is really following this this prototype calculation here. Okay, actually it comes from this matrix vector product. Okay, yeah. So main takeaway here is what? Okay, what's the main takeaway here? So the main takeaway here is if I gave you a linear transformation, okay, you need to go and cook out all the standard bases in your domain. Okay, so in this case, you have En of them, and then take your E, apply on each of them, and then organize them into a matrix. Any question so far? Yeah, okay. Yeah. Okay, so why it works? Why it works is actually coming from this kind of calculation. Okay, actually what you will get is a matrix vector. That's why matrix. Okay. All right. Okay, if no question, let's move on. Okay, let's move on. So now we're gonna introduce two ideas. One is onto, the other is one-to-one. Okay, let me give you a trailer first. This is a new kind of formulation of existence and uniqueness problem. Okay, we'll use function to solve a uniqueness and existence question here. So remember, when's the first time you see existence and uniqueness? You want to ask whether a linear system has a solution or not. If you have a solution, meaning it is consistent. If it's consistent, is it unique? Is it unique? Okay, so right. So let's see how this new formulation works. So a mapping. Okay, so this mapping actually is the transformation also. Maybe I'll add the word later. So all transformation function mapping, they refer to the same thing. Okay, same thing means what? I give you one thing in the domain, you produce one thing in the codomain. One input, one output. Okay, this is function. Okay, cannot be one input, multiple output. Okay, because this will cause confusion. I don't know where to go. Okay, one input, one output function. Okay, one input, one output function. So what's mapping here? So a mapping from Rn to Rn is said to be onto, okay, onto to the core domain. So here is a core domain. If everything, okay, if everything, so let's lock this up. If everything in the codomain is the image of at least one x. So meaning what? Anything I pick from the codomain, okay, there will be someone that get mapped to it. Okay, it's the image of some guy. If it's not onto, meaning there's something that's not hit by T. Does it make sense? Okay. So another word for onto is what we call a surjective. Okay, surjective and onto is the same. It's said to be surjective. So this word becomes surjective. Okay, onto the codomain or surjective. So in this case, this says that at least one, meaning what? There could be more x go to the same place. Okay, there could be more x go to the same place. So many to one is allowed. Many to one is allowed. Okay, so more things to the same place. I mean, this one I gave you an example, right? So just now I gave you, for example, let's say let's give you a map that's onto, for example, this map here. Let's say T from R2 to R. Sends what? Send xy to x. Okay. So this is onto. Why is this onto? So to solve onto-ness, you need to show me that. Give me everything, anything in my codomain. You need to show me something that maps to this. Okay. So if you give me x, so what's the thing that maps to x? For any x in R, what's the choice you can make that gets sent to x under this mapping here? What vector you can pick here? What vector can you pick that split up x? I think you can pick here. X and xx? Sure, you can use xx. Okay, for every x sends to x. Can you pick other choice or not? You can pick other choice, right? What are the other choice? x0. Yeah, x0. There are different points, you know. There are different points in R2. You know what happened? What happened if you make these two different choices? Let me draw to you. Okay, I mean, let me draw a bigger picture here. So let me bring everything down. Okay, so these two choices make a different story. So on domain side, you have R2, right? Okay, on the codomain side, you only have R like this. Okay, R2 to R, X and Y, X. Okay, so if you try to pick out XX, it means that you are picking out the diagonal line here. XX, ma? Sure or not? 1, 1, 2, 2, -1, -1. Okay, this line become the R line. But if you pick X0, where is X0? Where is X0? Which line? X0 is which line? X can change, 0 fixed. So it's the horizontal line. So this is the line that you pick up. Okay, so potentially, obviously, you can pick a different line. For example, what sort of line you can pick? Can you pick a different line here? What line can you pick? Can you pick different line? Any other line you can pick? For example, T of x1, maybe? Right. So x1 is what line? So it's the horizontal line, but shifted up by 1. Also can. Okay, so there's actually, so meaning what? There's more than one point in R2 that gets sent to the same point. Yeah. Okay. Any question? Question. So this line is x1, and this line is x0 for all x in R, for all x in R. And then this line is xx for all x in R. Okay or not? So you can see that actually this mapping is like picking out different lines here from R. If you look at the, so we say that this is a image, right? Image of this line. So if you look at a pre-image of this line, it's a multiple lines. And if you go backward, so how should we define it? Maybe we define it here then. Yeah. Where did we define the mapping just now? Px is called the image of x. And maybe we add a definition here, and x is the pre-image of Px. Okay. So if you have an x, you map it across. This is the image of Px. And then what's the pre-image of Px is the thing that maps into Px. So maybe make it more general here. Definition. Y in Rn is a pre-image of okay, x in Rn is a pre-image of y in Rm if t x equals to y. Okay. This is just some terminology here to use. Okay. Okay, so we talk about onto here. Okay, how about one-to-one? So one-to-one here is for everything inside your domain. Okay, there's at most one x that map to it. Okay, so there's at most one x that map to it. So such that tx is equals to. Okay, so this is one-to-one. So a very intuitive picture is like this. Let's say this is your Rn, this is your Rm here. Okay. So to say that it's one-to-one, for everything in Rm, there's only one thing that maps to it. If this happens, two things get mapped to same place, then this is not one-to-one. At most one x in the domain get mapped to Rm. Okay, if there's two things get mapped to the same thing, then it is not one-to-one. Correct or not? Okay, one-to-one. One-to-one. Okay. Sometimes we call it injective. Okay, so this is the second word we would use. Injective. Inject. Okay, so far, let's see another picture here. So if you have domain and codomain here, you can see that this one is not one-to-one because there's more than one that get mapped to one place. And then this is one-to-one because there's at most one. So, I mean, potentially, you could have a one-to-one map, but that's not surjective. So in this case here, this is not surjective. You can see that there's other point here is there's no pre-image. And there's other point there's no pre-image. But the point of one-to-one is what? At most one pre-image. At most one. If you have, you must have at most one. If you don't have, it's fine. Okay, so you could have a one-to-one map that's not surjective. And you could have a surjective map that is not one-to-one. because there could be more things get sent to the same thing, right? Okay. Shall we? Let's do some examples before we talk about general result. Okay, so let's look at this linear transformation here. So I'll give you a linear transformation. We can associate a matrix to it. So already solved for you, this matrix here. So before even looking at this question, judging from this matrix here, what's the domain and codomain? What is the domain and codomain? Still remember what we concluded just now? The n is the number of column. Okay, how many number of column here? 4. Okay. And then codomain has the number of rows. So what's the number of rows here? 3. Okay. So you see, matches up with this question. Does T maps R4 onto R3? Onto means what? For every, so let's write down. Let's write down this notation. I don't want to write for every, for any, this one. Okay, so it's an inverted A. Okay, for any B in R3, does there exist an X in R4 such that what? A X equals to B. Okay. So this is the meaning of onto. Everything inside your codomain must have at least one pre-image. Again, you see this? Familiar or not? Familiar? Asking about consistency of your linear equation. Okay, so let's try and solve this. And let's try and solve this. Okay, so this is a general B, right? So general B, we will write it as B1, B2, and B3 here. Okay. I think this matrix is pretty nice already, right? It is already in the echelon form. Okay, so we just need to make it reduced row echelon. So we need to do the backward phase. So can we quickly compute it? So we already found the pivot already, actually. So we just need to make 0 above these pivot position. Okay, maybe we can compute together. You can do your computation. I can compute also. Then we can check. Answer. Or you can check my solution also. Check my calculation. A bit looks a bit I mean, and then can you do continue? Just you need to scale it to REF. Try and check if the calculation is right. Yeah. Okay, so what did you see here? I think you get a pretty nice consistent system here. Right. So what's the general solution here? So either you can write it as a parametric form, or you just use you just write it as a equation also can. So what's the general solution here? So x1 equals to minus 6x3 plus b1 plus 2b2 minus 7/5b3. Sorry, which one is 8/5? Let me see. Which step goes wrong? You mean this step? So R1 plus 2R2. So this got minus 1/5, right? This got minus 6/5, right? Minus 7/5, right? No. 1/5, 6/5. Sure. Okay. Okay. So, and then x2 equals to half x3 plus half b2 minus 3/10b3, and then x3 is 3. Okay, because you only have 3 pivot here. Okay, and then x4 is equals to b3/5. Okay, you might see that there are x3. But remember that these b are actually already fixed. They are numbers. Okay, they are fixed already. There are some numbers. Okay, they are already fixed. We already fixed some b1, b2, b3. Okay. Those that can change is this S3. Okay, S3 is free. In fact, you must have at least one free variable. Do you notice why? Do you notice why? Yes, the row only have 3. You only have 3 rows. At most, you will get 3 pivot only. So at least one of them must be free. So in this case here, S3 is free. You could have more, but at least one. Because your number of pivot and most you can get is 3. Okay. So what's the conclusion here? So T maps are 4 onto R3 since the associated linear system is consistent. It is consistent. So you can find the pre-image. Okay. So you see, we turn a story about consistency into onto linear map. Okay. Any questions so far? So far, any question? Okay, if you don't want to solve all these, you can use theorem also actually. What theorem you can use? What's the theorem you can use here? There is a pivot in every row. Okay, remember that how to tell whether this has a solution or not. Okay, maybe I use Tuesday notes. So if you go to the Tuesday notes, Wednesday, I mean, where is it? If you want to use theorem also can. So you see, if you want to check that AX equals B has solution for all B, you just need to see that A has a pivot position in every row. Okay. Just now what we did is we also reached this stage. But after this stage, I tell you what is the solution. But in the case you just want to know whether there is a solution or not, then you can use this. But if you want to know what is the solution, then you need to solve it out. Yeah, this is the difference. Okay, not yeah. So if you remember this theorem, you can use it. If you don't remember, just calculate. Yeah. Okay. 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 We have second part, right? Check whether this is 1-to-1 or not. Okay. To show that 1-to-1s, kind of hard for the one that I told you. I mean, because for every x, you need to either tell me there's nothing get mapped to it or there's at most one thing. But to see that it is not one-to-one, what do you need to do? Find one point in your codomain such that there is more than one pre-image. Okay. Great. So one very one very obvious thing to try is 0 in your codomain. Why? Because you know that the pre-image of 0 must contain 0. The property of linear transformation is what? T will send 0 vector to 0 vector. So meaning 0 vector must be one of the pre-image of 0. So can you see another non-zero vector get sent to 0 vector? Is it easy to see? Is it easy to see or not? Well, I mean, you can cheat a bit, right? You can cheat a bit. I mean, we already do row reduction here, right? Instead of random B here, you should put 0, 0, 0 here. Okay? So if you put 0, 0 here, what happens? This part will disappear. But you still see a free variable happening here. So meaning what? This solution here is a solution to homogeneous equation plus the AS plus AS plus B solution. There is a homogeneous solution here, which is what? X1 equals to minus 6x3, x2 equals to half x3, x3 is free, x4 is 0. Okay? So if you put a different x3 into it, you will get a non-zero solution. Can you try one? Let's try one. So what is the non-zero x that gets sent to? So try x equals to, let's try 1. So let's pick s3 to be 1. The easiest thing to compute is x3 equals, when s3 equals 1. So minus 6, half, 1, and 0. So this will give, try this, and give, where is it? And give ax equals to 0. Okay. You want to verify together? Maybe let's verify together. So what is a here? A is 1 minus 4, 8, 1, 0, 2, 3. Okay, so I multiply 6 minus 6, half 1, 0. Okay. So, yeah. So what did you get here? Minus 6 plus 24. Okay, sorry. I think I did something wrong. So minus 6, 0, 0 plus minus 2, 1, 0 plus 8 minus 1, 0 plus 0, 0. Okay, so I think this one is obvious is 0. Okay or not? Okay. Yeah, so you can see that what can you see here? So this is a translation of your homogeneous solution actually. Okay. Yeah, so this measures out what we discussed last time. Okay, solution to AS equals to B is all the solution that you add with your homogeneous part. So the conclusion is since T minus 6 half 1, 0 equals to T of 0 vector, which is both of them get sent to the same place. Okay, so different things get sent to the same place, then T is not 1-to-1. Okay, yeah. No 1-to-1 is easy, but 1-to-1 is bit tricky. Okay, any questions so far? So far, any question? Maybe we continue this 1-to-1 and on-to business next lecture again. Okay, so to make your idea concrete, so we will do it again. I will tell you more about how to check 1-to-1 and on-to. For now, you can try a few exercises first. Okay, then next week we will talk about it again. Any question so far? Okay, if no question, we'll see you next week, next Monday.
Hello.
Okay.